of the main things that you'll be doing in school is doing a lot of practice on how to measure pH. There's a few ways that you can do this. So that's through indicators that I showed. That will pretty much give you a range of what the pH is. You also have pH probes as well. So if you just take the probe and put it in, your solution, it will give you an exact value. And then you also have things such as pH, pOH, which helps to calculate, like if you have the concentration of hydronium, you'll be able to calculate pH. And what is exactly pH is pretty much just a logarithmic expression of how much hydronium that you have. Don't write H plus instead of H3O plus because technically H plus doesn't actually exist in solution, and you can see that because the Bronsted-Lowry theory is a more recent theory. We don't actually use Arrhenius anymore. So pH is a measure of H3O plus, not H plus. And it's an inverse logarithmic scale. So I'll get into that further on. If you look at the various equations that you have here, it's a bit confusing, but I'll just explain through each one of them. pH is pretty much negative log 10 H3O plus in terms of concentration. And therefore, if you have a low pH, then that means you have high concentration of H3O plus. High pH meaning low concentration of H3O plus, so it's inverse. pOH is pretty much the opposite. So pOH is just negative log 10 OH minus. And pH and pOH actually have a relationship. So pH plus pOH is 14. So therefore, pH is 14 minus pOH, and pOH is 14 minus pH. Hopefully that makes sense. And if you just need to get the concentration of H3O plus or OH minus, all you have to do is pretty much just use a logarithmic equation and just convert it. So therefore, H3O plus concentration is 10 to the power of negative pH. So just remember your log laws. Same thing for OH minus. So for module 6, your module 2 molar ratio skills is really important in this case, and just knowing a bit of your log laws. So if you kind of forgot log laws, just make sure to revise it because it's really important. All right, let's move on. As usual, my computer is not working. Okay, cool, there we go. It is working. I do have a bunch of practice questions for you guys to have a go at. So let me just pull up the poll. Hopefully it works. All right, since we are short of time, everyone can have a go at the first 3 questions. And I know the answers are on the slide, but that doesn't mean, you just put the answer in. If you actually don't understand the question, let me know, and I am more than happy to explain. So once you get all the answers, just number them and just put your answer onto the poll. And if you don't understand, let me know. All right, so we have 2, 3.5, and 0.638. Does anyone else have anything else? Um, okay, looks like everyone's getting similar values. I'll just wait if anyone else wants to put in their answer. Okay, it looks like everyone's getting similar answers. So let's go through each one of them. I know the answers are up there, but it doesn't matter. Okay, so first one's asking, what is the pH of a solution of H plus being 0.01? So it doesn't matter if it's a H plus. If it's a question, just make sure when you're explaining it, you don't write H plus. Hopefully that makes sense. So if we go back, pH is pretty much negative log 10 H3O plus or H plus, same thing. So you just do negative log 10 on your calculator. So on your calculator, it should show up as log, and then you just plug in whatever the concentration is. In this case, it's 0.01, so that'll just be negative log 10 0.01, which is 2. Next one's asking, what is the pH to 2 sig figs of a solution with OH minus being 0.000316. So this is just asking pH. So if we go back, that's just negative log 10 OH minus. So you just do the same thing. You just do POH equals negative log 10 0.000316. And you should get 3.5 to 2 sig figs. And then someone is asking, what is a pH of 0.23 molar HCl? HCl will dissociate into H plus and Cl minus. So if you have 0.23 molar HCl, you'd still have 0.23 molar H plus because everything's in 1-to-1 ratio. So therefore, it'll just be negative log 0.23, which should get you 0.64. So that's how you kind of go through these questions. You should never get a negative pH value. If you did, then that means you did something wrong. So be very careful. And also just note that there's actually a negative in the front of pH and POH equations. So yeah, let's move on. You also need to know like your strength of your acids. In terms of strength, that's pretty much just how much does it ionize. So if it ionizes more, then that means it's a stronger acid. So strong acids ionize completely, which means you don't have an equilibrium. You have a forward arrow. So in the case of something like HCl, which is a strong acid, it'll just be HCl plus H2O going to H3O plus and Cl minus. Note that you react the acid with water to produce hydronium. And you can see here that acids are a proton donor, so therefore it donates this H ion, and it just becomes A minus, and the water accepts that proton and it becomes H3O plus. So that's how hydronium is being formed. Weak acids, on the other hand, do not ionize completely. The species are the exact same. You have an acid being a proton donor, water accepting it, and the H just goes over here to become H3O plus. However, you have an equilibrium because it does not ionize completely. And weak acids are pretty much in its molecular form. Most of them are in a molecular form. Something like acetic acid, for example. And if it's a weaker acid, then that means it sits more on the left than it does on the right. That means your Ka, which is your acid constant, is smaller. I'll get to that later. So if you're ever asked to compare, you know, which one's a stronger acid or which one's a weaker acid, you just need to look at your equilibrium expression, or like the equation that you have. You'll also need to look at Ka as well. So I will get to Ka. And it's not working. Okay. You will also just need to be memorizing your common acids and bases, such as your strong and weak ones. So for strong acids, it's pretty much just HCl, HNO3, H2SO4, H3PO4, and HBr. Note that H2SO4 and H3PO4 are strong when it first ionizes, but later on it becomes a weak acid. I'll get to that later. And weak acids are typically something like your acids that have halides in it, except HBr, so things such as HF, and something like carbonic acid, acetic acid, and HSO4, which is similar to H2SO4, is also weak. So I'll get to that later. Strong bases are things such as sodium hydroxide and potassium hydroxide, rest is weak. So your other hydroxides are weak. Ammonia is also a weak base. So yeah, just be aware of the different kinds that are present. All right, if we move on in terms of how acids and bases work in water, I've already explained how acids work in water. Water takes a proton from the acid over here, and there is a similar action that goes on in terms of bases. If you have a base over here and it reacts with water, the water actually becomes a proton donor, so it acts like an acid. So it gives one of its hydrogens to the base over here to become BH and OH minus. And water can actually act either as an acid or a base, and that's something called amphiproticity, which is another concept we will get to. You'll also need to know something called conjugate acid and bases. It's a bit confusing, but we'll just explain it in detail. Conjugates is pretty much what it becomes if it either accepts a proton or it donates a proton. So for example, let's say if you take HA and A minus. It starts off as HA, but it gives a proton to water, so it becomes an acid, and then the A minus is the conjugate base. Once it's given its proton away, it becomes a base. Whereas with water, water is currently acting as an acid, water is currently acting as a base because it's reacting with acid, and once it accepts a proton from the acid, it becomes a conjugate acid over here. So from a base, it becomes a conjugate acid. Hopefully that makes sense. And similarly, if you have your standard reaction where you have a base reacting with water, water in this case is acting as an acid. If it donates its proton to the base, you get your conjugate base over here as OH minus, and the base accepts a proton from the water, so therefore you get a conjugate acid as BH being produced. So that's how it kind of works. It's always going to be as pairs as an acid and a base. You will also need to know whether if a salt is acidic, basic, or neutral. So there's actually a way to work that out. So if you have a salt being given, so let's say something like acetic acid, you can see the equilibrium over here. Acetic acid reacts with water and it becomes hydronium and acetate. The first step is to figure out whether the ion is reacting with water. So in this case, you have hydronium and you have acetate. So you can see over here, that you have acetate, and you can see here that acetate is a conjugate base of acetic acid. So let's say if you have a salt, something like sodium acetate, and sodium acetate dissociates into water, you have sodium ions and you have the acetate ion. You know sodium is a metal. Metals actually don't react with water at all. They're just neutral. Whereas acetate over here is a conjugate base, and you can see that through this reaction. So therefore, you have a base being present within the water, so therefore the base would react with water to produce acetic acid and hydroxide ions. So therefore, sodium acetate will be basic. You also will need to know the strength of your ions. So for example, if you have a weak acid, you'll have a weak conjugate base. If you have a strong acid, you'll have a neutral conjugate. And what's the other one? There was another one that I wanted to say, but it's just not popping up in my head. I think if it's like, if you have a very weak, let's say acid or base, you produce a strong conjugate. So that's how it works. So yeah, that's how you determine the strength. Hopefully this makes sense. If you don't understand how this process works, let me know and I'm happy to explain it again. All right, let's move on. I don't know, again, why it's not working. All right, let me just scroll down. All right, so let's go through a few examples and we'll be able to work it out together. So, first step is looking at the salt. We have, in this case, NaCl. NaCl will dissociate into Na plus and Cl minus in water. You know that Na is a metal, so therefore it's neutral. And Cl minus is the conjugate base of HCl. It's a strong acid, so therefore Cl minus is going to be neutral. Neither of these are acidic or basic, they're neutral, so therefore the entire solution is neutral. I've already explained sodium acetate. So if we look at something like NH4Cl, so in this case, that's pretty much ammonium chloride. You just have to work out the conjugates again. So NH4Cl will dissociate into the water as NH4 plus and Cl minus. NH4 plus is the conjugate of NH3, and NH3 is a weak base, so therefore NH4 is going to be a conjugate acid. Cl minus is the conjugate base of HCl, like I've previously mentioned. Since HCl is a strong acid, Cl minus is going to be neutral. So therefore you have an acidic ion and you have a neutral ion, so therefore you will have an acidic solution. And you can see the reaction over here. NH4 plus reacts with water to produce NH3 and H3O plus. That's because NH4 plus is pretty much donating a proton to water. Hopefully that process sort of makes sense. All right, we also have something called proticity. Proticity is really important. So let's start off with actually what proticity is. Proticity is pretty much how many protons can it donate. If it's monoprotic, it can only donate one proton. So for example, HCl. If it's diprotic, it can donate 2 protons, for example, H2SO4. And like I mentioned, H2SO4 is a strong acid in the first ionization. However, if you look at in the second ionization, when you have HSO4 reacting with water, it actually is a weak acid at that stage. And you also have triprotic acids. That's something like H3PO4. So it can donate 3 hydrogens. And you can also see here that in phosphoric acid, you have the first ionization being strong, The rest of them are weak, and that's how it typically works for these two acids. So just be aware of it. And I've pretty much explained strength. That's pretty much what this section is exploring. And you also have something called amphiprotic substances. You've seen that water can act like an acid or a base, and that's pretty much what amphiproticity is. It acts like as either an acid or a base. And there are two substances that you would be encountering in amphiproticity. The first one is sodium hydrogen carbonate, and the second one is potassium dihydrogen phosphate. You can see here that sodium hydrogen carbonate pretty much just reacts with an acid, and when it's a base, it produces NaCl, H2O, and water. When NaHCO3 is acting as an acid in the presence of a base, it produces Na2CO3 and water. So just be aware of the different equations that you'll be encountering. So it's just good to be aware of it. And the HCO3 minus ion is amphiprotic. That's the main ion present over here. So if you're ever asked in an exam situation, like you have a spill going on and you need to neutralize the substance that's been spilled, what will you be using? You'll be using sodium hydrogen carbonate because it's amphiprotic, and it will work with either an acid or a base. And these are the equations you'll be writing for that. You also have strength of acids and bases, like I've mentioned, and you may be given questions where you have to visualize it. So in the case of, let's say, a strong acid, you'll know that it fully ionizes, so therefore you'll have only ions present. And you can see here that it's broken up into its ions. However, in terms of concentration, if it's a strong acid but it's dilute, you'll have a minimal amount of those ions, whereas if it's concentrated, then you will have several ions within a smaller volume. If it's weak, then you will have both the acid and the ions present, as you can see over here. And if it's dilute, again, you have a minimal amount. If it's concentrated, you have a larger amount. So just be careful in terms of strength and concentration. Strength refers to the degree of ionization. Concentration refers to how much of the actual species that you have present within the solution. All right. We'll also be looking a bit at titrations and dilutions. And you may be also asked to calculate what the pH is going to be if you have two solutions mixed. So that's when you have a mixture of an acid and a base being mixed. So this is pretty much just like your normal limiting reagent questions. So let's say you have, I don't know, NaOH and HCl mixed. You then first need to determine what the limiting reagent is, then figure out what is left over. So let's say you have, I don't know, 30 mils of 0.1 HCl left over in the reaction. So therefore, you can use that to calculate the number of moles of H3O plus or H plus, and then you can use that to calculate pH. You may also have changes in volume when you have two different solutions being mixed together, so just be aware of that in a question. And then once you have your moles being found, you then just use it to divide it by volume to get concentration, and then just plug it into the pH question. All right, this is a practice question that I've pretty much just included. And this is an example of a question that you may be getting. So let's look into it. It's asking what the resulting pH is, and it's saying that 250 ml of 0.33 molar HNO3 has been mixed, and it's diluted into 500 ml of 0.1 molar KOH, and what is the resulting pH. So all you have to do is pretty much use your limiting reagent knowledge that you have. So firstly, you know that it's HNO3 and KOH, so these two get added together to produce H2O and KNO3 as your salt. And then you just figure out the number of moles of each of them. So the number of moles of acid that you will have is 0.25 times 0.33, which is pretty much 0.0825. For base, it's pretty much 0.05. Everything is in a 1-to-1 molar ratio. Therefore, you just divide the number of moles of acid by the number of moles of base. So therefore, you have 0.0325 moles of acid remaining. HNO3 is a strong acid and it dissociates into H plus and NO3 minus. So therefore, the total number of moles of H plus you have is also 0.0325. You need to get concentration, so therefore you just divide it by the total volume. You have 250 mils and 500 mils, so therefore it's just 0.5 plus 0.25 and you get 0.043. Plug that into the pH value, so therefore it'll just be negative log 0.043 and you get 1.36 as your final answer.